Welcome. In this video I'll show that the minimum energy state for a magnetic field is the force-free field when it relaxes under the constraint that helicity is conserved. Now this has important consequences for magnetic confinement fusion. It's the principle behind the reverse field pinch configuration. It was proved by Woltjers. There's a paper in Royal Society Proceedings in 1958, and it's quite straightforward, but it shows you a nice application of the calculus of variations. So I'll review helicity, minimize the magnetic energy, and show that the result is a force-free field. And so what we're trying to do here is show that you start with some configuration, and the plasma can relax, and it can a small-scale turbulence, for example, interacts with the resistivity, and this dissipates energy. And so magnetic energy is converted into heat, and so the magnetic energy drops, but there's a constraint on the overall global helicity, and this is the twistedness, or how linked the field lines are. And so you say that the overall structure of the field can't change, the topology of the field can't change, but the small scale energy can be dissipated. And so we're minimizing the magnetic energy. So minimize this called W, so the integral over the volume of b squared, and then divided by 2 mu naught, and these are just constants, so we'll just drop them for the rest of the time. We have b squared, and this is integrated over the volume, and we're just using that b is curl of a. It's most convenient to do it in terms of a rather than b, and we have a constraint which is the helicity. So this is h, and it's the integral again over the volume of a dot b. See a previous video if you're not sure about this. So this is essentially a measure of how connected the field lines are. So if they're twisted, or if you have field lines which are linking through each other, this is a way of measuring that. And we're assuming that this is approximately conserved. And so what we're going to do is we're going to minimize, we're going to use the Lagrange multiplier method. So we minimize a different function called w prime. Here I'm just dropping the 2 mu naughts, so I'm just going to keep the b squared, and b is curl of a, so this is just curl of a squared. And then I'm going to integrate that over the volume. So that is the magnetic energy. And then I have a constraint, so I use Lagrange multiplier, and the constraint here is the a dot b, so the integral of a dot b over volume is constant. So this is integrated over the volume, this whole thing here. So I'm minimizing this, and you can apply the Euler-Lagrange equations, but it's a bit complicated because you have all these kind of curls and vector identities. It's easier in some ways just to do the variation. So doing the variation in delta W, and so this is this. So we have an A plus some kind of change in A, and then we compare that to the previous results. So W of A. So now what we can do is substitute this into here. So we substitute A plus delta A into these expressions, and then so delta A is small. So we neglect terms like here we have a delta A times a delta A. Neglect some delta A squared terms. So this, you can think of this as being a derivative. So if you divide through by delta A, anything with a delta A squared will go to 0 as delta A goes to 0. And so I just substitute this in here. So W prime. So this first term, so we have a curl of A times a curl of delta A. And there'll be 2 of those. And then there'll be a curl of A, which will be removed when we subtract this one. So this is just the difference here. And then the second term, well, we have a B, which is curl of A as well. So we'll have a lambda times A, and then here we'll have a curl of delta A. So A dot curl of delta A, and we'll have a lambda delta A times a curl of A, dotted with a curl of A. These are all vectors here, curl of A. So any term involving only a will be cancelled when we subtract this term, and any term involving delta a squared we're neglecting because it's a smaller term, which will vanish as delta a goes to 0. Okay, so now we can manipulate this and use some vector identities. So this first term here, that is a divergence, well, you can write this in terms of a divergence term, so there's a dot product in here. You can turn this into a divergence of, so delta A cross curl of A, and then you get a second term. If you expand this out, you get a second term. So delta A dotted. Now you have a curl of A, and this of course is just B. This bit is just B. So you end up with a curl of B in there. So this term here, you can expand as another divergence. So this is a divergence of a delta A crossed with A. And then you get another term, which is this delta A dotted with curl of A. You see it's essentially the same as this term here. But you have this extra divergence in there. Okay, so now we can group together some of these terms. So we now have integrals over the volume of two divergence terms, plus these two, which are essentially the same, and then plus that one. So I'll write this out again here. So I've just written these two terms here from the blue, and these two terms here from the red. And now when you integrate this over the volume, what you end up with is surface terms. So we can use Gauss's theorem to turn this into a surface integral. And then we just say that this is a closed system. So we have that the delta A is 0 on the boundary. So delta A, we're not varying the field at the boundary. So for example, if you have a conducting wall, so there's no flux through the boundaries, it's all line tied at the boundary, then we're not changing the walls. And so these two terms go to 0. So these two terms we can get rid of. And then these two terms we can group together like this. So we have a W prime now is, we'll just take the factor of delta A out the front. And we can drop the factor of 2 or just put it outside here. And then here we just end up with a term, so curl of B. And then plus, here we have a curl of A, so this is just B times a lambda. And this dotted with delta A. And then integrated over the volume. And so this must be equal to 0 if we're trying to find a maximum or a minimum. So we're minimizing at the minimum. So we're doing a variation of A to find the minimum value of this function here. And so for any value of any perturbation A, this must be 0. And so the only way that can happen is if this is equal to 0. And so therefore we must have curl of B plus some constant times B equals 0. And that's just a force-free field. And this just says that the lambda here is connected to the conservation of helicity. So if we want to work out for a given case, we need to find a solution, work out what the helicity is, and then you can write this lambda in terms of helicity. But the general result is that this is true. This is what the field relaxes to, where lambda is a constant, which only depends on the initial configuration. And so this is useful in many situations where you have a relaxing field, such as in reverse field pinches, or spheromax is another example, where you inject a plasma and it relaxes to form closed field lines, and then you can use this relationship to predict what that will be.